tell us about non-commutative lower bounds.
Hi, thank you for coming to the organizers for. So I'll this will mostly be a survey talk, just because I'm so that because I assume that so that it's more accessible to more people. But if anyone wants details of any of the proofs, I'll be happy to talk about it. Okay. So yeah, and so as complexity theorists, everyone wants to attack this question, and just like various branches of complexity theory would attack this question in different ways, like something I've learned during this workshop, that proof complexity would like to would attack this by asking the NP versus co-NP question, or meta complexity would ask whether DMC's problem is NP hard, or in bounded arithmetic, what I understand, please don't catch me on this, whether whether the P not equal to NP statement is consistent in some theory. Similarly, in algebraic circuit complexity, we want to attack the P versus NP question by asking the VP versus VNP question. And in particular, it's a natural stepping stone, because if you believe that P is not equal to NP, then under the under GRH, we also believe that it has to be that VP is not equal to VNP, and is therefore a much simpler question. And that's the central goal of algebraic circuit complexity. So what are these classes that I spoke about, VP, VNP? So the basic computational model in this field is the algebraic circuit, which is it's been defined before, but I'll just repeat the definition. It's a directed acyclic graph in which the leaves are labeled by variables or some field constant, and the internal nodes are labeled by addition or multiplication gates, and therefore naturally any node in this graph computes a polynomial, and the polynomial computed at the root is said to be the polynomial computed by the circuit. So in particular, this circuit computes this polynomial. So, and the objects of study is in this field are polynomials over n variables in general of degree d, and as in most complexity theory fields, we want to give lower bounds on the size of the smallest circuit computing some explicit polynomials. Okay, so it is, again, as usual, it is easy to see that most polynomials require really large size circuits. This comes just via counting arguments. And what we want to show is that there exists an explicit polynomial. I won't define what that means, but essentially it's like an explicit polynomial is a polynomial in VNP, such that it cannot be computed by circuits of poly ND size. So poly ND size circuit, polynomials computable by poly ND size circuits is what VP is. Okay, we want to separate. And what is known quite a bit in this talk, I'll just there are many restricted classes, as was mentioned in Anama's talk, but for now I'll just talk about constant depth circuits. And recently in the breakthrough result, it was shown that the first super polynomial lower bounds were shown against constant depth circuits, and in particular for depth 3, the lower bound is n to the omega root d. Although constant depth circuit lower bounds are known in the Boolean setting, what makes this really exciting in the algebraic setting is that we actually know very good depth reduction results in the algebraic setting, which is not known in the Boolean setting. In particular, we know that a poly-size circuit can be reduced to a depth product depth 2 circuit by blowing up the size to s to the root d. And also, in fact, it can be reduced to product depth 1. So the same as depth 3, some power, some product, some circuits. Also, by blowing up the size to s to the root d. And therefore, you see that this, at least at product depth 1, the lower bound is tight. So, yeah. However, in the general setting, if that's for arbitrary depth, the best lower bound continues to be not that great. It's just n log d due to a very old result of Baur and Strassen. Yeah, so we know the best possible thing for constant depth circuits. General setting, it's not that good. So there are other restricted models that we would like to study. In this talk, I will focus. So we've already seen VP and VNP, but we'll talk about two other models, one of which is formulas. So formulas are similar to circuits, except that the underlying graph is only allowed to be a tree instead of a DAG. And polynomials, which can be computed by poly-sized formulas, is said to be the class VF. And it turns out that there's another very natural class called VBP, which lies in between VF and VP. And apart from the VP versus VNP question, I mean, extremely important question in algebraic circuit complexity is like whether each of these inclusions are tight or not. So again, in general, so this VF, I have added a few more things, but so very recently, like this year, it was shown that that VF is actually equal to VF log D. What does log D mean? It's depth log D. Okay, so VF is equal to VF log D, and in general, you can start thinking about formulas of smaller and smaller depth, and yeah, so the result I mentioned showed that VF constant depth formulas are separate from VBP because the hard polynomial turned out was actually in VBP. That was what LST had shown, and in general they actually show a hierarchy in the constant depth regime. So for any constant delta, they show that there is a separation between these two classes. Now, what can we say outside VF? It turns out that the best thing you can show, for example, between VBP and VP is just like n polylog n versus n square separation. That's the best thing you can say about here. And between VP and the best lower bound against VP is just Baur Strassen. Okay. So as the title slide says, the focus of this talk is going to be on a restricted setting called which is the non-commutative setting. Okay, what is the non-commutative setting? Here, the multiplication gates they respect order. Okay, so non-commutative circuits, they are essentially the same as commutative circuits, except that multiplication gates now respect the order. And the question is, can we do something better in this setting as compared to the commutative setting? And so let's just relook at the things that we mentioned. The depth reduction statement is the same, but the separation between formulas and VBP, it works for root log D instead of log D. So in the commutative setting, they could show a separation for delta for depth up to log D, whereas here they have root log D. And also they show that if you consider homogeneous formulas and ABPs, then there's a separation. Like, this is all in the non-commutative. And most remarkably, which is where this thing started, this Nissan in 1991, which is also the result that Ido had mentioned in the morning. Using his lower bound, he could show that that there is a polynomial in BP which is not contained in this class BP. So in the commutative world, the lower bound is, the separation is like n log square n versus n square, whereas here it's an exponential separation. So there's something in BP which requires exponential sized ABPs. And also in this setting, we have very good hardness amplification results, which are again not known in the commutative setting. So it seems, so in the non-commutative setting, we seem to have a lot of because of the extra structure that we have, we can exploit them actually, and which is why I think this is like a very exciting domain, because at least to me it feels like, we should be able to solve a lot of the important problems, at least in this setting. Okay. And so now that we know that Nissan has already proved the separation between these two, for the rest of the talk, I would like to focus on like what is happening in VP versus VNP in the non-commutative setting, and also between VBP and VF. What is the status? So what? Oh, yeah. So what is the status of VP versus VNP? So unfortunately, the best lower bound that we know against non-commutative circuits continues to be the same thing that we know for commutative, which is Baur and Strassen. Okay. So what we asked is, can we at least do better if we assume that the circuits are homogeneous? Okay. And yeah, recently we could show that we could improve this lower bound from n log d to nd. Okay. So this is, and it's actually, so till d is about this, and beyond that it becomes n log d log n by log d or something, but essentially n. And again, this polynomial actually has a better upper bound if we don't have the homogeneity restriction. So this is again giving a very slight separation, but between homogeneous and non-homogeneous circuits in the non. So I will just give a slight proof overview of this, and which will also help me tell you about the usual template for proving algebraic circuit lower bound. So in general, what we do is we define a measure such that such that if a polynomial is being computed by a size s instance of some model, then the measure is small. So it's small in terms of NDS. And for the given polynomial, it's large, right? And that allows us to give a lower bound on S. And so what is the measure that we use? So suppose F is a homogeneous non-commutative polynomial of degree D, then we define Fi to be polynomials. So note that because it is non-commutative, there is this additional notion of position, right? So because the order is important. So what we do is that we say for a given non-commutative polynomial Fi is the polynomial you get by setting the variables in position I and I plus 1. To keep those and set everything else too. Okay. And then we look at the rank of the space generated. So for example, if you had just F was just sum of two monomials, then which is x1 through xd plus xd to x1, then F of 1 is going to be x1 plus x2 plus x1 x2 plus xd plus 1. Okay, so we are not focusing on the variable number, it's the position number that. Sorry. Yeah, this is d minus. Yeah, and the main lemma is very simple. As you can see, the measure is quite simple, and in fact, you can't get the highest this measure can be is like D. Okay. And the main lemma of, is that we say that this measure is at most S if it is being computed, if there's a polynomial which is being computed by a size S homogeneous non-commutative. So once we have that lemma, what we do is that, so how do we, so as I said, the highest this measure can be is D, but we managed to get an ND lower bound. The way we do that is by using this trick of Baur and Strassen, where they say that if F is being computed by a circuit of size S, you can compute all their partial derivatives simultaneously without blowing up the size much, just a constant factor. Okay. So we have to prove a homogeneous version of that, which is doesn't take, yeah, it's a little bit of work, but it's not very difficult. We managed to do that. And again, because we are working in the non-commutative setting, partial derivatives is with respect to the first position, but our thing works even in the general homogeneous setting. And we can show that if a polynomial is computed by a homogeneous circuit of size S, then the usual partial derivatives can be computed with only a 5S. And once you have that, you note that our previous lemma didn't require continues to work if you assume that there are multiple outputs, doesn't need it to be a single output. And you show that for our hard polynomial, it is actually getting the lower bound. This is the proof overview. So now I will try to see, I had mentioned that there is this hardness amplification result known in this setting, right? So does our lower bound says, give something better than what we say using these things? It turns out that we can't get anything which is really better. Why? Because what CILM says is that if you have an n to the omega by 2 plus epsilon lower bound for some polynomial over n variables of degree d, then you can improve the lower bound by increasing the degree, reducing the number. So you get an improved lower bound for another polynomial which has now fewer number of variables and degree which is much better. Okay, but so now and now how much the improvement you get, it starts degrading as the degree, as this degree becomes larger and larger. So as if d is constant, for example, which is the version I had written, this improved lower bound is exponential. If d is poly in n, then this is just poly in n. But either way, so what is the lower bound that we have? It is nd, right? So for CILM to start kicking in, we need degree to be n to the epsilon. And for that, the improved lower bound that you get is not, it's worse than nd. So it doesn't really make sense. So which brings me to like questions which would be very interesting is that and can possibly like solve the VP versus VNP question in the non-commutative setting, is that can we show a lower bound similar like it can't be ND, but basically can we show superlinear lower bounds for when the degree is sub polynomial in n, like not n to the epsilon, but something smaller than that. In that setting, can we show superlinear lower bounds? If we can, then CILM will start kicking in and we start getting like much better lower bounds then. And secondly, can we have hardness amplification statements which work better when D is large? Then again, a statement that we have would start giving much better load. Okay, so in the VP versus VNP question, I think these are like very interesting questions which I have thought about a little, but yeah, it would be very interesting if either of these two. Okay, and that's all I want to say about the VP versus VNP in non-commutative setting. And now I will spend like a couple of slides on the VF versus VPP question in the non-commutative. So this Ido had mentioned this in his talk, but let's, as he mentioned, I mean, this is a remarkable, easy to prove result, and I'll just mention it again. So San showed that if you have a polynomial of degree d, and you consider this matrix. So what is the matrix? So for any I, you can write all possible monomials you can of degree up to I, and all monomials of degree d minus I in the column. And what is, so for the entry in the M1, M2 element in M1, M2 position is going to be the coefficient of M1 times M2 in F. Okay, and he showed that for any I in between 1 and D, the number of vertices in the ith layer of the smallest ABP computing F is going to be exactly equal to the rank of this matrix, which makes it like, we don't really get to see exact characterizations of size in complexity variables, which makes this a really nice result, and therefore gives like tight size bounds on for any polynomial. And so using this, you get an exponential lower bound for against ABPs and hence formulas for a polynomial which is in, so this is actually in VP, non-commutative VP, and this gives you a separation. Okay. But so in some sense, we already have formula lower bounds in the non-commutative setting, except that this works for ABPs, and which makes the question of VF versus VBP in the non-commutative setting extremely interesting. And till very recently, actually, there had been hardly any progress towards this question, but in the last 2-3 years, there has been a lot of progress. So as I had mentioned, so in the non-commutative setting, like this year, it was shown that you could depth reduce to log depth without increasing the size by more than polynomial factor. And it turned out that in the paper, Nutan, Srikanth, and Sebastian showed that up to root log d, I mean, there's an order here, root log d, you can show a separation. Okay, so you know how to depth reduce up to log d, and you know how to separate from log d onwards. So the question obviously is, can this gap be closed? Okay, and so beyond log d, you would expect that you can't, you would expect that the blow up starts becoming super polynomial, but like what, like how do these two interact? It's very interesting. This is one way. And the other thing is, in the same paper, they show that in the homogeneous setting, formulas and ABPs are separate, right? And the point is that this lower bound is not tight. So this lower bound is n to the log n for a degree n polynomial, actually the iterative matrix multiplication of degree n. And the point is that if it had been tight, then you would have separated not only VF and VBP in the non-commutative setting, but also in the general setting. If their proof would have, yes.
Yeah, about this text. This a formula is already a log depth, right? Log d depth. So what is log is? I think log s. Oh, it's log s and it's log d.
So actually, d is the not necessarily. Sorry, it's the what's it called?
The syntactic. Yeah. But this was already. I thought it's already.
Yeah, it should have been, but it wasn't there somehow.
the circuits, but
Yeah,
formula, I don't think it was.
it was with their formula. Yeah, log S is known, but this was somehow not. Okay, yeah, so and if this would have been typed, so either if this, yeah, if it had been into the log n for the same polynomial, we would have been done. Okay, and the point is that this proof works in a slightly more general, what do I mean by unordered setting? So in the this is the last. Non-commutative setting, as I mentioned, the position matters, right? So in some sense, you can think of variables appearing in position I to belong to a bucket I. Okay, and their proof actually doesn't. So this proof, this one uses it, but this one does not use the fact that in the non-commutative setting, the buckets actually come in an ordered fashion. Okay, so the point is that can we use the additional fact that it is ordered to actually improve this lower bound.
Mean that for the polynomial against which the lower bound, the polynomial has the
Property that yes, the polynomial has this because it is homogeneous. The polynomial has the property, and in the because the formula is homogeneous, you also have that the if it's a non-commutative formula, it is respecting the order. But this works as long as you assume that things appear, like things from a bucket appears only once. It doesn't use the fact that it is ordered as well. And this was some problem. This ordering thing is why I had also tried to attack this question, and I could show a separation between NP and a different sort of a structured formula in which the formula is assumed to respect the order. Okay? But so you have buckets. I won't define what this is. It's a made up sort of thing. But essentially the idea was that in the non-commutative setting, if you assume that the polynomial is ordered, then and you additionally assume that the formula is ordered, then can you show a separation, which is what I could do, except that again the same thing. So it turns out that if you had a super polynomial separation between homogeneous formulas and ABPs for a polynomial that has degree log n, then you would be done. Okay, but their proof works only for degree n. So in the similar way, in this setting, the degree is log n, but the number of buckets in some sense is n. And if the number of buckets was log n, then again it would have separated VF and VBP in the non-commutative setting. So it seems like I don't know. I mean, ever since this paper had come out, the hope was that, assuming this additional ordered setting, maybe we will be able to separate VF and VBP. And I still hope that we should be able to do it soon. And because we are in a proof complexity and meta complexity program, I would like to give 2 additional open threads, which I haven't really thought about. So don't ask me too much about it, but they seem very interesting. And so one is that you could ask, are there VP natural proofs for VP and C? And because of CILM, even proving if VP natural proofs exist for these circuits of size which are super linear for low degree, that also becomes interesting. And are there any connections between proof complexity lower bounds and lower bounds in the non-commutative setting? We know that there are in the commutative setting. The only one I know of is this non-commutative IPS, which which doesn't lead to anything because we already know formula lower bounds here. But especially this, yeah. But are there any more?
Time for a couple of quick questions.
What was the ordered formula in 2 slides before? So, I mean, if it's ordered, also ordered and non-commutative, it seems to me the same, or ordered and non-commutative. If it's ordered,
No,
it's even
yeah, so
weaker
the-
than non-commutative.
No, or yes, it is. So yes, it is weaker, which is why proving lower bound just for that is not enough. But the hope was that we can make it, so
I'm just
homogeneous.
saying that ordered, you don't need to say it's non-commutative.
When you're saying that if it, yes. Like it makes sense only in the non-commutative.
No. But, and you can have a polynomial and say, I want it syntactically to order like the products so that they will respect some order. But the polynomial is non-commutative. It is commutative, sorry. It's just a syntactic constraint.
That is true. I mean, so in the formula, you need it to be, so the polynomial, actually, I don't think I'm understanding. So you're saying that if the polynomial is commutative and what do you want?
Then I'm saying that, no, I was just trying to understand the ordered and non-commutative, which seems to be the same.
It's not the same. So it's not exactly the same in the sense that, so if you had homogeneous non-commutative thing, then you know that if your buckets was just what are the variables appearing in, so bucket I suppose would be variables appearing in position I.
Oh.
Okay, and in that, in the homogeneous non-commutative, the homogeneous non-commutative formula respects the order. Okay, but I wanted it to like generalize this in some way where you are allowed to define buckets, and suppose your polynomial is such that it respects the ordering of the buckets. Okay. The non-commutative formula now does not have, I mean, why in the computation it need not be respected. There might be cancellation.
Right.
So whatever the class that I defined, that was where formulas were respecting the ordering in this. And it turned out that if the number of buckets was log n, then you could convert it to formulas of that type, which is essentially the same proof as like why you can make it homogeneous when the degree is small. But I couldn't prove it for log n number of buckets. I needed the bucket to be large, similar to how LSP or CLS needed the degree to be large.
Let's take
Yeah.